Welcome to Maths with EJD. In this video, I'll be showing you the Python code for the Barabási-Albert model, which is a very good example of the scale-free networks. So remember the key properties of the Barabási-Albert model are the fact that they have a presence of hubs. When you say a hub, it's basically a place of high concentration of edges. So their hubs are nodes with disproportionately high connections. And I gave the example of social media. So on social media, you can see hubs as influencers or celebrities that have very great following. Okay. Then another key property of the Barabási-Albert model is the robustness to random failures or vulnerability to targeted attacks. And I can explain that to mean still in the context of celebrities and influencers, right? They have a great following. They get a lot of advantage by being celebrities and influencers. But then because they are so visible, they can be easily trolled by even people they don't even know and all that. So we can look at it in that regard. Then the third property is the degree of distribution following the power law given as P of k tending towards k raised power minus gamma, where gamma is typically ranges from 2 to 3. So those are the key properties of the Barabási-Albert model, being an example of scale-free networks. Okay. So, and to implement that, right, you have the Python code right there. Of course, we use the NetworkX, which is the library for graphs and networks in Python. And of course, Matplotlib is to show us what the graph looks like at the end of the day. So two major parameters are needed here, just like in the case of the Erdos-Renyi model. For the What-Strogatz model, three parameters were required. We need the number of nodes, the number of, I think the number of immediate neighborhood nodes or something like that, and the probability and the rewiring probability. But in this case, all you just need will be the number of nodes and the new edges you want to reach by the free scale network. Okay, so here we take number of nodes to be 100, and we want the new edges to be reached to be 2. That's number of edges to attach from a new node to existing nodes. So we can play with both the number of nodes and the new edges to see what the graph ends up looking like. So in line 9, that's exactly where the Barabasi graph is drawn. So you have scale-free graph is just a variable name, but the actual thing is happening at the other side of the equality. That's NX. NX is network X. So Barabasi underscore Albert underscore graph is actually like a function or a module, if you like, in the network X library in Python, and it takes parameters, number of nodes and new edges as declared in lines 5 and 6. So from lines 12 to 15, that's where you are putting all of that together to actually visualize the graph. So let me just run this so we can see what that looks like. Okay, so this is it already. If you run it again, it will, okay, I mean, before we even go, so you can see that there are two nodes here in the center. They have high concentration, whereas you have other nodes that don't have as many concentrations. So you can see these nodes as like the celebrities or the popular airports like Dubai airports, like Atlanta airports. And of course, if you're in a place like Japan, maybe you're talking about like Osaka, Kyoto, or Tokyo airports like that, compared to other airports, in places that are not that popular. Okay. So just like I said, we can play with these two parameters. So let's do that. So the first thing I like to do is I want to take the simplest number of nodes so we can easily probably figure out what's happening. So imagine if I take, of course, we can't have one. Let's say if you have two nodes, okay, we have two nodes, we just have, okay, that's not possible. So Barabasi-Albert network must have m greater than or equal to 1 and m less than 2 and all of that. So, but we can't have two nodes. So maybe three should work. Okay, three does work. Okay, so three does work. So we have this. Then let's take it to like four nodes and see what happens. Okay, for four nodes, see what happens. So you still have this influencer person connected to three nodes like that. So that's basically the essence of the Barabasi-Albert network model. So uh you have one person, one node that has so many connections. So see how this goes. Two edges. So if I take this to 6, okay, this is what we have. So that's if it must be attached to two edges. What if the number of new edges should be 3? It is going to change the shape a bit. See what that looks like now. Okay, so let me go to 7 and see what happens there. So 7 with 3 edges, this is what it looks like. If we take it back to 2 edges, imagine what it looks like. So 2 edges. Okay, so this is what it looks like. So each node yeah, you have 2 new nodes coming into the play. That's what this is about. So what if we do 8 still with 2 edges? Okay, what if I now change the number of edges to say, let me just go to 6. Okay, so that shapes it a bit. So it looks we have this interesting shape. Okay, what if it's just 4, half of the number of nodes? Okay, yeah, we have something like this. Then let's do this. Let's say this is 9. Say this is 9. This is what it looks like with 4 new edges. So if we want to do 2 new edges that we started with, this is what we have. And then we can just keep playing with this. Say this is, let me say this is 8, for instance. Let's just see what that looks like. Okay. Wow. Okay. So it's like a radial kind of thing. All right, so let's do 7 and see how that affects anything. Okay, you have this star kind of thing. Let's do 6 and see what happens. 6. Okay, okay, this is so cool. Um, so let me take it to 10. Let me take it to 10, and we have 6 edges to be connected. Okay, we have this. Okay, now let me start going up to 20. So we go to 20. Okay, beautiful. 20. How about what if I do 2010? 20 new nodes and 20 nodes and 10 new edges. So this is what happens. So let me now take this one to 30. So this is 30. Okay. Now, I mean, in all, you still keep seeing that there are some people in some nodes in the center that have very high connections. Those are the influencers and celebrities in the context of social networks. So, still on it, let me go to 40. So we have something like this. Let's go to 50. 50. So something still like this. So now that it's 50, can I take the number of new edges to say 30 and see what happens? 30. Okay. Oh wow, this is cool. This is so cool. Okay. This is lovely. I mean, you can if you can even try just checking out networks for fun. It's so beautiful. It's borders on artwork. So we have, let's go 60 and see what that looks like. Okay, 60 is like this. Then 70, 70 is like this. 80, 80, something like this. Okay, 80 is like this. How about 90? 90 is like this. Then, of course, the popular 100. 100 with 30 new edges. This is what it looks like. Good. So let me try something. How about 100 new notes? And I mean 100 notes and 100 new edges. What does that look like? Okay, that's impossible. That doesn't work. Okay. How about if I say 90, 90 new edges? Wow, this is lovely. This is so cool. 90 new edges. This is so nice. This is so lovely. Okay. So let me take this down like 80. Okay. 80. So you have this radial kind of thing happening there. So 70. Okay. Let's do 60 new edges. 60 new edges. Okay. Lovely. Okay, let me go to 50 and probably just stop there. Yeah, so this is all that. So very nice. So with this, I come to the end of network models. Of course, the graph and network theory series still continues, you know. So you can look forward to other things under graph theory, under graph and under network theory, I think mainly, but of course they're all together, right? So subscribe to this channel. Um, you know, hit the notification bell so you can get alerted each time a new video is released. Comment, let me know if you want me to take a topic or solve a problem. And don't hesitate to like and share so that more and more people can have access to this great learning. Till I come your way again, keep connecting, keep networking. Bye.